Variational autoencoders have allowed modern image and video generation models to reach unprecedented levels of quality and speed. They do so by compressing the petabytes of data we throw at these models into a representation that's easier and faster to learn from. If you go to Hugging Face and look at any recent open source image gen model, you'll most likely see a VAE folder in the weights repo. This tool has become commonplace in this space. Today, I wanted to build a simple VAE from scratch, but in a more unique way. Most tutorials immediately dive into the math and throw a bunch of equations around, but here, we're going to start off with the code-focused approach, and slowly piece together the parts one by one. We're going to run into many errors throughout this video, which hopefully make it clear why we do things in the way that we do. And we'll get more familiar with PyTorch along the way. Don't worry if you're a math enthusiast though. We'll briefly revisit what we uncovered through the mathematical lens at the end. Also, this video doesn't serve as a replacement to the mathematical intuition, but rather just a supplement. Today's code isn't resource intensive at all. In fact, I can run everything on my base M1 MacBook Air. And as usual, all the code from this video will be linked down below. So what is today's task? Well, let's say I gave you this specific dataset and asked you to generate more samples of it. I was able to use some simple code to generate this data, but typically we wouldn't have that luxury. But first, why might we even want to generate more data for a distribution that we have some data points of? Well, each data point here is two-dimensional, but imagine our data points were much higher dimensional, as in the case of these flowers. If we're able to sample more points that follow this flower distribution, we've essentially generated new images that look as if they came from the original dataset. The hope is that if a model is able to generate flowers that it hasn't seen before, it truly understands the elements that make up a flower, such as the petals, sepals, pistils, etc. Sure, it wouldn't know the parts by name, but it still would understand these components at a deeper level than just arbitrary pixel patterns on a screen. So how do we even go about this seemingly daunting task of generating new data? Well, sampling directly from this dataset is difficult because we don't have any equations representing how this data was created. However, sampling from a simpler distribution like the normal distribution is only a single function call away. Is it possible to map our complicated distribution to the simpler normal distribution? Here's another way to think about what we're doing here. Let's say I'm moving apartments, so I hire some movers. The square footage of my apartment is most likely going to be larger than the square footage of the truck. As the movers load up the truck, it really doesn't matter to me how they pack my possessions as long as nothing is damaged or lost. The movers have to play Tetris with all of my furniture and boxes, but as long as I see everything of mine in my new apartment, I'm none the wiser about how they did it. Given that movers aren't cheap, especially in California, we'd expect our movers to bring with them some experience and intuition for how most efficiently to pack the truck. For example, they'd probably want to pack the larger furniture first and then move on to the smaller items. We expect our model to perform a similar task here by compressing the nuances of our original dataset into the simpler bivariate Gaussian distribution in whatever way it deems most efficient. Let's see what intuition we're able to instill in our VAE. Here is a simple neural network with a couple of linears and ReLUs that take in a random point from our dataset and maps it to a bivariate normal distribution represented by 4 values, 2 means and 2 standard deviations. We'll assume that these normal distributions are independent of each other, or that our covariance matrix is diagonal. In this video, we'll be working with PyTorch's distribution objects, which you can think of as probability distributions that have learnable parameters, along with other useful methods such as for sampling. In order to create our torch.distributions.normal object, we're chunking the outputs of the encoder into 2 tensors, one for the means and one for the standard deviations. Since our standard deviations must be positive, I'm passing them through the soft plus function. Also, in our context, the unit bivariate Gaussian can also be referred to as the prior distribution. The prior belief we're imposing onto the model is that the original dataset is structured enough to be represented by this specific distribution. It may seem arbitrary, but for a good prior, we want an easy to sample from distribution. However, if our prior is unreasonable or too restrictive, then the model won't actually be able to perform that well. But how can we verify that our encoder network successfully encodes values from our circle distribution to the prior distribution? Well, we need a way to map back from the prior to our circle distribution to verify the encoder's work. Let's create a second network. We'll take in 2 values again, but this time representing a sample from our bivariate Gaussian and output 2 values as well, hopefully representing a data point from our original circle distribution. Now, before we get to training these networks, we need to initialize them, the optimizer, and the loss function. For the optimizer, I've just defaulted to Atom, and for the loss, I've chosen MSE because we want to minimize the distance between our input data and their outputted reconstruction. For each epoch, we zero our optimizer, pass our tiny dataset through the encoder, and then sample from the bivariate Gaussian distribution that the encoder returns. Hopefully, these samples have some semantic meaning regarding our original dataset that the decoder can then extract. So to verify, we then pass these samples into our decoder to get our reconstructed data. After calculating the mean squared error, we backpropagate our loss and step our optimizer. The first graph is our original circle dataset. The second graph is our encoded latent space, or the outputs of our encoder. These two look exactly how we'd expect. Remember, we want the latent space to follow our prior distribution, which in this case was the unit bivariate Gaussian distribution. After passing the encoder outputs to the decoder, we get the third graph, which is our reconstructed data. If our encoder and decoder did their thing, we expect the reconstructed data to match our original dataset. The fourth graph is some generated data. Since our latent space is hopefully a unit bivariate Gaussian, we theoretically should be able to take samples from it and pass them to our decoder to get samples from the circle distribution. And yeah, we failed at that. This was the code used to generate the graphs though. For the second graph, since our encoder network's output is a torch.distributions object, we have to call .sample on it to actually get points we can plot. For the decoder, we then pass in these sampled points from the encoder. Finally, in order to generate new data, we can just sample from our prior distribution, which was the bivariate unit Gaussian, and then pass them into the decoder. We don't actually need the encoder when it comes to data generation. Back to the issue at hand, what went wrong? Well, several things, but first, there's a pretty serious bug in our code. It's due to the fact that our code relies on some random sampling. Taking a random sample from a distribution isn't a differentiable operation. I mean, think about it. The whole point of backpropagation is to be able to calculate how much to nudge our network parameters in order to minimize a loss value. If we randomly sample from a probability distribution, there's no deterministic way to tune our network parameters. It would always change based on what random value we sampled. This means in our code, when our encoder outputs the bivariate Gaussian and we sample from it, we're essentially breaking the autograd graph. So after we call loss backward, the gradients don't flow to our encoder. Adding the following prints better illustrates this issue. The gradients for our decoder look fine, but the gradients for our encoder are none. So how do we fix this? Well, let's take a look at this diagram. A normal distribution is parameterized by a mean and a standard deviation. Using these two values, we can take a sample. The blue circles represent nodes that contain a random operation, or one that's not differentiable. During backpropagation though, indicated by the red arrows, since there's no deterministic effect that mu and sigma have on z, the autograd graph breaks. However, if we isolate the randomness to another node in our autograd graph, we can sample from the unit normal and then multiply by our standard deviation and then add the mean in order to transform the sample to the correct normal distribution. Now, no matter what epsilon is, we can calculate the relative effect mu and sigma have on z, allowing us to tune those parameters as we wish. So making the following change in our code allows our gradients to flow as expected. However, for even cleaner code, we can just replace .sample with PyTorch's .rsample method, which automatically samples from the unit Gaussian under the hood, keeping the parameters of our bivariate Gaussian still differentiable with respect to our loss. Now, after rerunning our training loop, we can see that the encoder is now receiving gradient calculations as expected. After fixing this bug, let's take a look at our results. Well, now that our training is working correctly, what we can see is that our encoder and decoder have just learned the identity function, because technically that does minimize the MSE loss. In fact, if we take this smiley face and pass it through the encoder, we get pretty much the same thing as the output, except with a slight transformation. The decoder then undoes this trivial transformation. This also explains why our generated data looks just like the bivariate Gaussian. Our GPUs are just too expensive to be learning the identity function. So what's next? Our encoder's outputs have strayed too far away from the bivariate unit Gaussian, meaning that it's now useless to take samples of the prior and pass them into our decoder. We need another force to constrain the output of our encoder to align better with our prior, requiring the encoder to learn a function that's more complicated than the identity. Well, how can we do that? What if we add another term to our loss that penalizes the encoder if its output is too far away from the prior? However, in order to do this, we need a way to calculate the distance between our prior and the probability distribution the encoder outputs. Enter the KL divergence. It's the measure for how different two distributions are from each other. The pair of distributions that look more alike will be the pair with a lower KL divergence value. We can easily verify the result with some PyTorch code. This means if you thought the left pair had the lower KL divergence, you'd be right. Conveniently, our encoder outputs a PyTorch distribution object which we can pass directly into the torch.distributions.KL divergence function. Since we want to constrain the encoder's output to be close to a bivariate unit Gaussian, we can pass that in as our second parameter. Since we have a unique bivariate Gaussian for each of our data points, we'll end up with a separate KL divergence value for each one, so we use .mean in order to get an average. When we rerun our training loop, our results look like this. It may not seem like we're making much progress, but I promise, we are. We can see how the output of the encoder is once again a bivariate Gaussian, but this time without any autograd bugs in our code. But it's not perfect. There's one final piece of the puzzle. When we added the KL divergence term to our loss, we're setting the importance of it and the original reconstruction term to be equal. However, if we wanted the reconstructed data to be higher quality, we can downweight the KL divergence term with a new hyperparameter beta, which will be a number between 0 and 1. I set beta to 0.75 and got this. We can see how both the reconstructed data and newly generated data seem to be slightly cleaner than when beta was set to 1, and setting beta to 0.5 yields this. Our generated data actually resembles our original data set. There's one final piece I really want to hammer home here though. Note how after we added the KL divergence term and we tuned beta, the latent space exhibits an amazing property. Even though the latent space as a whole follows a bivariate unit Gaussian, the colors are actually appearing to be somewhat organized. The mean and variance for each color isn't exactly 0 and 1 respectively. This is because if for every point our encoder outputted a mean of 0 and a variance of 1, our decoder wouldn't have any signal in order to generate data from our original data distribution. This really is the crux of a VAE. While it learns to compress the data, it also organizes them in the latent space, allowing for samples from different parts of the latent space to contain semantic meaning that the decoder can then decode. Also, everything we covered today scales to data of much higher dimensions, like images. Let me add a couple of convolutional layers to our encoder and decoder so they're better able to understand images. The actual training recipe remains exactly the same as what we've already covered. I won't go through each thing here, but everything will be linked in the description down below. After training on the MNIST dataset with a latent dimension of 64, our reconstructions look like the following, and our generated images actually look reasonably realistic. This means our model learns to compress a 784 dimensional image into just 64 dimensions, over a 90% reduction in size. Before we end things for today, I wanted to revisit our loss equation. This is actually referred to as the evidence lower bound. Most resources will derive this mathematically, but today we saw the exact role each component of this evidence lower bound plays from a code-first approach. The first term represents the log probability of our data. If we reframe our decoder's outputs to represent the mean of a multivariate Gaussian with a fixed covariance, and the original data point to be x, maximizing x's likelihood is equivalent to minimizing the MSE between our encoder's outputs and our original data point. The second term is exactly the KL divergence term that we've added to our loss, the one between our latent distribution and our chosen prior, which for this video has been the bivariate unit Gaussian. The log probability and the KL divergence terms are at odds with one another. If we want perfect reconstruction, our model simply learns the identity function. If we want the predicted Gaussian parameters for all of our data points to be exactly the bivariate unit Gaussian, then our model doesn't learn how to effectively reconstruct our data points. Technically, Q of z given theta and P of z both do not have to be a bivariate Gaussian. You can always calculate or approximate the KL divergence between any two distributions. We simply chose to go with a learnable bivariate Gaussian for our encoder's outputs and the bivariate unit Gaussian for our prior. If you guys choose to read more about VAEs, which I highly recommend you do, you'll definitely come across more of this math. But hopefully now you've gained a little bit more intuition behind why the parts of this equation are necessary. I'll link my favorite resources down below. Perhaps the most exciting part of all of this is that the research space for VAEs is still incredibly open-ended. There's a lot of new directions, such as how to maximize compression for even faster video generations, to new architectural changes, to even adding more semantic understanding into our VAEs, for example via text captioning. Well, if today's video was helpful, I'd love to learn more about it in the comments below. However, I'm really excited to share my next video with you guys, and until then, take care.